3% speak about dynamos in rotating spherical fluid shells. Please.
Yeah, I first want to give some introduction to this problem. Here we have our basic equations. We use busse approximation. That's the divergence of velocity vanishes. So it's actually motivated more by the Earth's core than by solar applications, because in the Earth's core the density doesn't vary much across the core, and the incompressibility is a good approximation. The equations, of course, are familiar to you, and we have want to minimize the number of parameters, so we have only the Rayleigh number, the rotation parameter, and the two Prandtl numbers. The kappa is the thermal diffusivity, and lambda is the magnetic diffusivity. Now, since we have this constraint, we can use the general representation of divergence-free velocity fields in the terms of poloidal and toroidal component, and the same for the magnetic field. And we then use the spectral code, represents velocity of the poloidal field, say in terms of spherical harmonics, and for the radial dependence we use the Chebyshev approximation.
And the physical meaning of the decomposition.
Yeah, I should perhaps say that the radial velocity is essentially given by this v, and if we take the radial component is given by the two-dimensional Laplacian. L2 is times v, where L2 is equal to minus d2 by the phi squared times 1 over sine theta squared minus 1 over sine theta d by d theta. I hope I got it right. So that these are spherical coordinates. And while the W is really the curl of U, and the radial component is equals to L2W. So that's the physical association with this, and of course similar to the magnetic field.
So excuse me, you were using the Euler potentials for the velocity?
Yeah, it's not an Euler potential, it's just it's a double derivative, of course, here, and so. The boundary conditions, we want to make the problem simple, so we use stress-free boundaries to avoid the complications through Ekman layers, and we, of course, assume that the limit of high rotation rates will not make much difference whether you have a no-slip boundary or a stress-free boundary. We also assume that the temperature is fixed at the boundaries. I mean, this could be changed. It's relatively easy to change. And we also assume that at the boundaries the magnetic field matches the potential field outside. That means the outside of this shell is assumed to be insulating.
What is this gained by this decomposition?
D of U and D of B is equal to.
It's complicated.
Yeah, no, it's actually one advantage is if we take now the equations and take the curl of them, and then we don't have to deal with the pressure anymore. We eliminate the pressure, and we have then equations which in the spectral way can be evaluated very simply.
One question.
Do you have temperature gradient between outer and inner cylinder?
Yeah, I mean, actually there are two possibilities. I mean, we have either heating from from below, from this cell, and just no heat sources inside here, or we can have heat sources inside here and have homogeneous heating of the whole interior, including the inner boundary. This doesn't make too much difference for the problem.
Yeah, one question. The joule and viscous heating is omitted here.
Yeah.
Is this a good approximation for the Earth?
Yeah, that's very good.
Although the field is strong?
Pardon?
Although the magnetic field is strong, comparatively.
Yeah, I mean, I think it's still a good approximation. It's actually, in keeping this busse approximation, we actually have to assume that the ohmic and viscous heating in the heat equation can be neglected. I mean, this is sort of part of the busse approximation.
Oh, that's compelling.
Yeah, that's consistent with the busse approximation.
What is the difference between busse and incompressible?
And incompressible,
Yeah.
here's the same. I mean, whenever you have thermal buoyancy, you speak of busse approximation. Naja, the whole problem is sort of described in this way. Sort of, you start off with convection, and then you have magnetic fields possible in two basic forms. I mean, they can be either symmetric with respect to the equatorial plane or antisymmetric, and this is a quadrupolar mode, and that's called the dipolar mode. And if one then also looks at the periodicity around the equator of the convection columns, then one has, in the simplest case, 8 possible symmetries of the dynamo solutions. If one starts just with the azimuthally m-periodic convection columns. If there are other hydrodynamic bifurcations preceding the onset of dynamo action, then of course we lose symmetries, and but in principle we can look at this bifurcation structure as in terms of symmetry consideration and see what kind of solutions are possible. I don't want to dwell on this because later on you will see that solutions are chaotic anyhow, so it doesn't make too much sense to the just of mathematical interest, I guess. Yeah, if one looks now at the solutions where we can get dynamos, we and this is done in conjunction with Radostin and Simitev. His thesis he worked out not only for Prandtl number equals 0.1 but also for other Prandtl numbers where you get dynamos, and typical diagram is of this form. We have the Rayleigh number here for onset of dynamos as a function of the magnetic Prandtl number in this form, where as you lower the magnetic Prandtl number, you must increase the Rayleigh number in order to keep the magnetic Reynolds number approximately constant. The magnetic Reynolds number for onset of dynamos is between 50 and 100, and this explains this slope here. Beyond this line you get dynamos, below we don't have dynamos. But there is another boundary for dynamo action, which is caused by the fact if convection gets too rigorous, then we have flux expulsion, and we can no longer expect amplification of the magnetic field. So there is a boundary up here as well, and then we can characterize the dynamos. For instance, in this case we have either chaotic dipoles, as indicated by the red symbols, and here we have more hemispherical type dynamos, and at higher Prandtl numbers we may also get quadrupolar dynamos. So the shape of the dynamos, the structure of the dynamos depends on.
The dynamic Reynolds number was constant.
Yeah, the onset for dynamos is given by a magnetic Reynolds number of the order between 50 and 100.
What's the dynamic Reynolds number?
The hydrodynamic, yeah, that's the same, except for the magnetic. If you divide the magnetic Reynolds number by the magnetic Prandtl number, then you get the hydrodynamic Reynolds number.
So you increase it, right? So
you divide, you multiply it, excuse me. If you multiply the magnetic Reynolds number with the Prandtl number, then you get a constant, the Reynolds number of the flow increases here, and the magnetic Reynolds number is about constant here. The magnetic Reynolds number is about, say, 50. Yeah, I just
because convection velocity increased, right? That was the reason.
Yeah, convection
becomes faster.
So this is an example of quadrupolar dynamo, which is always oscillatory, and
You're upside down.
it's upside down. Okay, yeah, doesn't make much difference. Still looks the same way. And you see there are always new flux, toroidal flux tubes generated near the equator and moving out towards higher latitudes, and in this way you get essentially half a period from here to here, and now it's almost a full period here.
Do you show here distribution of magnetic field or
Yeah.
velocity field?
No, that's magnetic field.
Magnetic
This
field.
is the radial component of magnetic field, and this side is the azimuthal component, the mean azimuthal component of toroidal flux is given here, and you see it's always pushed towards higher latitudes as you go on in time. Time goes down.
So this is strongly non-axisymmetric.
Yeah, this is essentially chaotic behavior, but still the mean magnetic field dominates, so you have this oscillatory quadrupolar magnetic field.
It looks like some particular mode of convection is dominant.
No, the convection
is dominant, no?
is always this columns.
But what the M value?
M value, that's a high M value, usually say of the order 12 or so.
So it's selected somehow by this or by rotation rate? Or
No,
by-
it's
by-
convection is relatively little influenced by the magnetic field. It's just essentially the same without magnetic field, except that, we discussed this on last Friday, that if the magnetic field, if the differential rotation becomes too strong, then you have those oscillations. But these are eliminated by the magnetic field, and we have.
And the flow is selected by the depth of your shell, right? Horizontal structure is the same as vertical, probably.
Yeah, no,
The tangent cylinder is influencing.
Pardon?
The tangent cylinder, as you say, for the depth, is influencing your convection.
You see this even here, that the tension cylinder is influencing not only the convection, which is much stronger outside the tension cylinder than inside, but also, of course, the magnetic field generation is predominantly outside this tension cylinder.
But what Sasha said about the rotation rate influencing the dominant M, that's also true in the linear part.
Yeah,
of course, this is a non-linear computation, so you fill up the whole spectra. But it's clear that as a function of your rotation rate, the number of downflow lanes you have along the equator is somewhat sensitive to the rotation rate.
Yeah.
But here you show quadruple mode. This is a mode with a minimum growth rate.
Actually, this quadruple mode comes in only at higher Prandtl numbers. I mean, Prandtl number of the order 1 and higher.
And so growth rate has a maximum for this mode, yeah? Or
No. I mean, it depends now on the. Yeah, so here the Prandtl number is 5, so it's different from the previous slide. And then you get, if Pm is low enough, it's less than P, you can get quadrupolar modes as preferred one, yes.
as preferred.
Yeah. I mean, you can also get hemispherical modes like this one, and they are also oscillating, and this occur at somewhat lower Prandtl number. They are preferred, say, for magnetic Prandtl number still lower than P, and you see that.
But you don't have graph like growth rate versus M.
I mean, these are actually chaotic nonlinear solutions. There's no growth rate in here.
Oh, I see.
There's no kinematic problem. I mean, you may be familiar with the fact that at the end of the Maunder minimum, in the Sun, there was a quadrupolar field observed, in that the people found there at just at 1700 that sunspots occurred only at the southern hemisphere on the Sun, and only at the end of the Maunder minimum the usual butterfly diagram came up again. And so hemispherical dynamos are not that
Calculations to this.
Huh?
How do you relate your calculations to this, to dynamo?
No, I just want to point out that there's a competition between dipolar, quadrupolar, and hemispherical dynamos. All three different kinds may exist. I mean, if you think of the magnetic field of the outer planets, we may well have some quadrupolar fields there, because the dipolar field looks very strange, and cannot be understood in terms of simple dynamo theory. And whenever you have a probe flying by the outer planets, then of course you see only the dipolar field, the dipolar component, even if it's the smaller one, because the quadrupolar field decays much faster than the dipolar field, and that's why the field you observe with your space probe is not characteristic of the dynamo.
But in the case of Earth, that in paleomagnetism is any signature of different modes.
Yeah, okay. I mean, in the case of the Earth, we clearly have a dipolar.
Dipolar. I think we always have dipolar.
And if you measure energy of the mean magnetic field,
yes.
So this is comparable with what energy? Energy of rotation or energy of what?
No, it's comparable with the energy of convection.
Of convection.
Kinetic energy.
Kinetic energy. Okay, so this is equipartition.
In
some sense.
Yeah, I mean, usually the magnetic energy is somewhat lower than the kinetic energy, but it can come up to the value of kinetic energy.
You can show again your plot, with this magnetic field lines. I didn't understand this hemispheric. I thought it was two different cuts. You show it's kind of striking, this difference. So we refer to hemispheric. What on the left pitches on the
yeah, on the left, the upper part, we have the different rotation here. We have positive prograde different rotation on the outside, activate on the inside. Here is the cross section of the equatorial plane. You see that's the columns here.
Oh, it's a different cross section. Okay, so
and yeah, I should have explained this more carefully. Here you see that's the mean toroidal flux, And here's the polaroidal field, of course, as indicated here. And yeah, that's all what we see on those three.
So why is it concentrated in one hemisphere?
Yeah, I mean, it has advantage that the influence of the magnetic field on the convection is for the same strength is larger, because the magnetic field influence of the convection goes quadratically. And for the convection, because it has the form of the columns, it doesn't make any difference whether you have the magnetic field operating in the upper hemisphere or in the lower hemisphere. And especially, I mean, this is true for the different rotation, because we had already learned that the magnetic field is important in breaking the different rotation, reducing the different rotation, and it seems that this is done more efficiently with the same, say, with the same magnetic flux, if they have the concentration of the field in the upper hemisphere instead uniformly throughout the sphere.
So in your calculation, something broke the symmetry, and why symmetry is broken in your calculation? You had spherical harmonics, and suddenly everything is in one hemisphere.
Yeah.
What was the physical mechanism of breaking the symmetry?
Now, yeah, this mode is just the superposition of a dipole and a quadrupole.
Exactly, that's the main point.
Yeah. But the physical reason, I think, that this configuration is preferred is this fact that the action of the magnetic field on the velocity field, especially on the different rotation, goes with the square of the amplitude of the magnetic field. And therefore, if you can concentrate the magnetic field, then of course, for the same amount of magnetic flux, you get a stronger action on the different rotation.
So you put a seed field in this configuration, right? Because you know that. I'm puzzled because you have a symmetrical problem and suddenly becomes asymmetrical.
No,
Yeah.
I
So
think-
what was
I mean,
wasn't
if I
hemisphere
can
preferred here?
if I can intervene, I mean, there are some theoretical work by Stefan Fogg in NS, and they are showing that, of course, in this kind of hemispherical dynamos that Fritz is getting, very likely that you have excited the quadrupole mode as much as you have excited the dipole mode. And it's clear that in the attraction and the limit cycle, they have been showing that also for some work with the VKS2 experiment. It seems that, and that's a question we need to answer now and look with perhaps production and destruction of the dipole and the quadrupole family. It seems that in the parameter regime that Fritz is hitting in this simulation, the strength of the two are of the same order, dominate all the other modes, and there is a cancellation effect on one hemisphere and a strengthening on the other.
Yeah, but actually just from point of symmetry, because we have northern and south symmetrical.
Both
You
modes
should
are
respect-
symmetric. Both
should
modes are
respect,
both modes are symmetric with respect, or anti-symmetric with respect to the equator. I'm just saying that it's a question of relative strength, and they have been showing in the geodynamo, in the inversion with observation, they have been showing that the difference between a reversal of the geomagnetic field and an excursion of the geomagnetic field, it depends on the relative strength of the dipole and the quadrupole. So when you have a reversal, you have a quadrupole that dominates when the field is slipping. Well, when you have only an excursion, the dipole is always dominant. So I think what's going on is that in certain parameter regime, you trigger and excite both the dipole and the quadrupole, and there is a cancellation effect.
Okay, but this is in principle laminar type of dynamo, and in this dynamical system there is appearance of chaos, and this is the reason for reversals.
No reversals here, right?
This equation.
You see
Yeah,
reversals?
yeah, this
So
oscillates.
I see reversals here because we didn't mention this.
What is the reason for reversal? Appearance of chaos in dynamical systems.
No.
No?
I have my own theory for reversals.
But how you have reversals here? Just flipping or not?
Yeah, this is just sort of
Okay, then it's clear. Yeah.
really periodic oscillations, real periodic oscillations which go on here.
Okay.
But did you look as you change the parameters of your simulation and you capture the hemispherical dynamo? Did you check if the relative amplitude of the L equal 1 versus the L equal 2, of the odd L versus the even L? Did you see a change in the amplitude of these modes in your spectra? Could we look at the spectra of this solution and see if there is a change in the relative strength of the odd versus even modes?
No, not usually. I mean, when we plot this, we get diagrams of the form that the L equals 1, it's like this, and the L equals 2 would be just similar. I mean, they are a phase for the hemispherical dynamics.
What is the period of reversals?
Yeah, I mean, I wouldn't call this reversal. It's just sort of an oscillation.
More oscillations.
Yeah.
What's the period of
And the
this?
period is the magnetic diffusion time.
But this is regular oscillations or chaotic. Is it possible to
It's
distinguish?
fairly regular. I mean, you see
Regular,
here
okay.
the new flux of the other sign appears at the equator and then grows and pushes the older flux towards the higher latitudes, so that at the end, I mean, we have just here just half a period. Here you see that in terms of the colors, this is the reverse of what you started off with.
You have oscillations just in only one hemisphere, yes?
Yes.
Oh, you don't have reversals because.
No, Sasha,
Only
you
one
can see
hemisphere.
on the sign.
I see.
Yeah.
I thought in Gary's experiments, he has actually intermediate phases where he has a tilde dipole.
You mean what's mine?
Yeah, but he has only dipole oscillations essentially, or dipole reversals.
Another question, he is often talking about solutions that he has where the magnetic energy strongly exceeds the kinetic energy.
Yeah, in certain parameter regimes, I think that's especially, when he uses, I mean, he uses often very high Prandtl numbers. Prandtl numbers in the original Klarsmeier-Roberts paper was 900. So then, of course, you can get magnetic energy which exceeds the kinetic energy.
And you agree then?
Yeah, I mean, we find the same thing. Yeah.
How do you find the seed field here in the simulations?
I mean, we don't need, I mean, we get this state, whatever initial conditions we.
Okay, but if you have a seed field very small,
Mm-hmm.
do you have linear stage of instability or it's purely nonlinear effect?
I mean, if we have the Rayleigh number high enough, it starts from infinitesimal seed fields, the dynamo. At lower Rayleigh numbers, we may have dynamo only at a finite amplitude of magnetic field. I mean,
It's
I
nonlinear
showed
effect.
this example on last Friday, you
Mhm.
remember,
Yeah.
when we, for small magnetic fields, we couldn't get a dynamo. Yeah, here's just a graph where we find dynamos as a function of P and of Pm, and here's a dipolar sequence. Here there are some hemispherical ones, and here for lower Prandtl numbers there's quadrupolar dynamos. There's sort of some mixed types where we can't really decide what the symmetry is.
And this Rayleigh number, it's what unit in the sense, so 10, 15.
Yeah, that's actually, in
Multiplied
our
by-
Rayleigh numbers, is probably 10 to the 5.
10 to the
5
5.
times this number.
Okay.
You don't go below 1 with your magnetic Prandtl number?
or we have been going below 1. I mean, then we find still dynamos if we have the Prandtl number also very low. So this could be extended to Lohmann Prandtl number. We just haven't done it because it gets too messy the slide.
Yeah, but for this value of Rayleigh number, this is just excitation in a linear stage of evolution. Dynamo in a linear stage.
Yeah. I mean, but we could go to small amplitude magnetic field. I mean, especially it's a higher Prandtl number. It's easy to go from very low magnetic field strength to rather high magnetic field strength. You can cover the whole range of amplitudes.
What uncovered here, the point, these uncovered circles.
This is no dynamo. It's an empty one. Here we have, for instance, near the boundary, we can have the effect that dynamos exist only above a certain amplitude magnetic field. Now this is above a certain Rayleigh number. Yeah, the lower one is of course clear. But beyond a certain Rayleigh number, the flux explosion takes place and we lose the dynamo. So near the boundary, the dynamos exist only in a certain finite range of the Rayleigh number. Yeah, we can of course also look at the energies and find diagrams like this here. Here we have a comparison between the kinetic energy and the magnetic energy, and in this case you see the kinetic energy is still much larger than the magnetic energy, and what we can see is that the magnetic energy saturates. If we have the Rayleigh number too high, the Rayleigh number is shown here at the bottom, then the dynamo sort of saturates, and especially the mean part, that is the axisymmetric component of the magnetic energy, decays actually. And this is
but it is still low amplitude limit, yeah?
Pardon?
This is still low amplitude limit for excitation for dynamo.
Yeah.
In the sense that it's not.
It's for this Prandtl number. I mean, the magnetic energy never get very large, never beyond the kinetic energy, I should say, and that's why, yeah, you see this effect here. I'm just wondering what I have.
But it should be principal difference between two kinds of dynamo. I mean, dynamo which arises in a linear stage, and dynamo due to the nonlinear process. Excitation of dynamo. Or you have linear instability in this system, or you don't have.
He's asking supercritical or subcritical
Yeah.
application.
Yeah, in this particular case, we have a supercritical bifurcation. You see the magnetic energy. This is at least the dipolar part. I mean, I should have pointed out, this is the quadrupolar component, this is the dipolar component. The dipolar part starts from 0 and just grows here until it finds saturation. The quadrupolar part comes in only at some higher value. You see that here's the ohmic dissipation compared to the viscous dissipation, and they are also, I mean, similar in their ratios to the energies. So,
this connection, I have a question. Do you find that if you make the magnetic Prandtl number small, that you can, numerically speaking, make the fluid Reynolds number larger than otherwise? Because most of the energy is now dissipated through the ohmic channel.
Yeah. low magnetic Prandtl number, we actually have to make the energy of convection higher in order to get a dynamo.
And you can do that numerically.
Yeah,
You can actually go to higher fluid Reynolds numbers. than
yeah,
otherwise.
that's possible. I mean, in the regime, I mean, we have to lower the Prandtl number then. We have done dynamos for Prandtl number 0.1 and magnetic Prandtl number 0.1, and we have then can still numerically get using conversions. Now, one thing which is perhaps unusual for the turbulent system is that you can get the different states depending on your initial conditions. And this is shown here. We have here two dynamos. One is on the mixed type, on the left side, and we show here the quadrupolar component, and the dipolar component in this case is relatively weaker than the quadrupolar case.
This is as a function of time or what?
It's a function of time, yes.
Mhm.
It's time. And there's another dynamo which is purely quadrupolar dynamo. If you put in some dipolar components, they will decay. So there, in this case, we have an example where the kind of the realized dynamo depends on the initial conditions. So in this case, perhaps it's not. No, yeah, I think it's still surprising us. But the other examples.
What are different curves here?
Huh?
What are the different curves?
The different curves is, I mean, we always show the fluctuating toroidal field by the its energy by the blue line, the poloidal fluctuating by the green line, and the mean toroidal flux is given by the red line, and the black line shows the mean dipolar, the mean poloidal
Yeah.
field.
But it looks like very nonlinear.
Yeah, yeah, this is certainly a highly chaotic system.
What really number here?
Oh, if I would know, I mean, this is perhaps a few times 10 to the 6.
10 to the 6.
What's the period of rotation of this unit?
I mean, the tau parameter is, I think, in this case, is 10 to the 4.
10 to the 4. So because periods when you have no dynamos, then again it's excited.
Pardon?
Because number minimum here.
No. This is a dominant component. The quadrupolar field is indicated here, and it has amplitudes here of 200, 400, and so on, while the dipolar is only sort of a smaller contribution. But you see that this quadrupolar field is different from this quadrupolar field. Here the quadrupolar field has in the mean higher amplitudes, and it has the character that any dipolar component which is superimposed on it will decay if it's sufficiently small.
But you said that it's not chaos. Just
No, I said it's chaos.
it's chaos.
Yeah.
Just appearance of
It's
chaos.
chaotic.
And you determine the threshold of appearance of chaos in for example, in Rayleigh number.
Yeah, it's a slow Prandtl number. The threshold to chaos is fairly close to onset of convection. It becomes convection becomes on twice the critical Rayleigh number is already chaotic.
Oh, okay.
Now, the main point I want to make today is that the dependence on the Prandtl number and the magnetic Prandtl number of dynamos is a very important aspect. And this is usually not realized because people usually, for simplicity, assume that Prandtl number and magnetic Prandtl number are both equal to 1. They justify this, they say the turbulence will cause eddy diffusivities, and this eddy diffusivities will be of the order 1. but it's important to realize that the most you can say will be of the order 1. They could still vary by factor 2, 3, 4, whatever, maybe 10. And what I want to point out is that the dynamos change their character dramatically if you change the Prandtl number by factor 2. For instance, here we have the Prandtl number 1, and we have dynamos which are characterized by very high fluctuating magnetic field energy divided by the mean, the energy of the mean field, while for higher Prandtl number the mean field becomes much stronger, and you get, for this ratio, you get this values as indicated here. And now this was our early finding. We then, of course, realized that there might be hysteresis aspects to this dynamos.
So what do you mean? So on the right, this is the Prandtl number.
This is a Prandtl number.
And here, this is the ratio between Prandtl and magnetic Prandtl number.
Yeah, yeah.
So when you go, so it means your Prandtl number comes larger, so you are going toward larger PM.
In this direction, we go to larger PM. Yes.
Okay. And so, in all cases, you see that it's growing. The overall field is growing, and now this is a ratio of the two energies. Okay.
Yeah, yeah.
And you see that as you make your PM larger, you find that there is more energy in the fluctuating field.
Yes.
And as you reduce PM, less.
Yeah, at least
For a
that
given
depends on the Prandtl number. In this case, the ratio
trend
doesn't change as much.
Yes, the trend seems to be the same. Now
Yeah.
that's interesting. So let me write that down.
Fritz, and you speak, when you speak about hysteresis,
Yes.
you change Rayleigh number or...
We change everything.
Yeah, but I understand, but when you speak about hysteresis, there should be some diagram. If you increase parameter, you go to one trajectory. If you decrease parameter, you go to the another trajectory. This is the definition of hysteresis.
Yeah.
And
Okay.
you observe this is just...
Now maybe I show right away this
yes.
final results. Here we see that there is that this jump which we saw can actually be continued. That the there's a highly fluctuating magnetic field exists at the same time for the same parameter values as the dynamo with the high mean magnetic field, as indicated by the blue symbols. So the jump that you saw before actually is only sort of occurring, say, right here. But if we we can continue the highly fluctuating magnetic field dynamo much further to higher Prandtl number in this case, and find this region where both dynamos exist.
Yeah, but when you speak about hysteresis as versus the Prandtl number,
Yeah.
in the sense it's not the same physical system, because what you change,
Yeah, okay.
you change just material of the system when you change.
Yeah.
So it's not real
Yeah, maybe we
hysteresis
should
in a real system.
point out this situation in the Rayleigh number.
This is physical.
yeah.
Except that we could not get high enough so that this dynamo, say, would jump up to the fluctuating one, which we expect to happen. So here we have two different dynamos, just as in those cases, and they exist at the same Rayleigh number, and here just for some given values of Prandtl number, magnetic Prandtl number. And what's interesting now, and that's sort of crucial property of these dynamos is that their heat transport is always the same. I mean, these dynamos are very different in their structure and their character, but they both are equally efficient in transporting the heat. And this is, I think, points to the fact that what controls the amplitude of dynamos is not some equipartition or whatever, but it is the amount of buoyancy energy available. And the dynamo that is realized must be one which optimizes the heat transport. And it just happens in this case that there are two different dynamos which both optimize the heat transport, they both lead to the same heat transport, and that's why they can both be realized and be stable. They are both attractors, and this is a situation which you normally would not find in purely hydrodynamic systems. There you always have one turbulent state, and you would be very surprised if you open your water faucet and get a different turbulent state with different amount of water coming through there.
I'm happy to that. How do you trigger that? How do you actually succeed to get this blue dot or red dot?
Yeah, it depends on the initial condition. What we put in as our initial condition for the simulation.
So that I missed. How do you do that? What do you do?
Now, yeah, we usually take dynamos for different parameters and then change the parameters and continue the simulation. But I mean, it really depends on what kind of initial condition you have. If you have a dynamo which has a strong magnetic field, strong Lorentz forces, then you will get usually into this high mean magnetic field into this state. When the dynamo is more feeble, and then you get into this state. I mean, I should perhaps show these two different states as indicated here. I mean, here you see that the mean magnetic field is very high in this case, and so this corresponds to the blue dots in the previous graph, while the red dots correspond to a magnetic field. In this case, it's very low, and the fluctuating components of the magnetic field are also still lower than in the high magnetic field dynamo. But you see sort of a reverse property for the kinetic energies, especially the differential rotation. In this case, the high magnetic field case is suppressed a lot, and that is of course due to the braking action of the Lorentz force. While in the other case, the differential rotation is still quite noticeable, but certainly not so big that it would affect convection very much. It would not lead to localized convection or whatever we saw before. We can see this when we shut off the magnetic field. When we shut off the magnetic field, we come back to the relaxation oscillation, which I discussed on Friday. And you see in both cases the same oscillations. They are still chaotic, of course, but they have the same heat transport and so on. And which shows that there are two ways to optimize the convective heat transport. Can do this with a relatively weak magnetic field, but then you have higher differential rotation, which you know is not good for heat transport, or you can do this with a high magnetic field where you suppress the differential rotation, but you also suppress to some extent the convection by itself, I mean the fluctuating component of the velocity field. But both effects amount in the end to the same heat transport.
Are you able to start from scratch and get this different state?
Yeah, I think if we could, I mean, to get to the state, we need to put in a finite amount of magnetic energy initially, and depending on how much mean axisymmetric state component we put in, we get either this state or this state. If we put in little, then of course we get state like this. If we put much more, then we get.
That's interesting.
Get,
I want to try
this
this
state.
exercise.
But this is not yet reversals. Yeah? This is
Pardon?
it's not reversals.
No, there are no reversals.
Yeah.
If I kind of make a somewhat unphysical assumption that my Prandtl number can be changed like temperature by just turning a knob, then what you are showing in the last view graph seems very much like a first order phase transition.
Yeah, we could call it
So
that way, yeah.
would it be possible to say that if I define an order parameter by the mean magnetic field, by the fluctuating magnetic field, then I would see first order phase transition like behavior, and then I may see actually that near the transition the dynamics will slow down?
No, I don't think that is the case. I mean,
One of the characteristics of first order
I don't think
transition is slow down of dynamics.
it does not. This aspect is not reflected in this dynamos. I mean, there are other aspects which one finds near the onset of convection. If you have convection and here's the Rayleigh number going on, then what you find is there you have either hexagons or you have holes. And when you look at the stability, you find that holes are stable up here, and hexagons are all the way stable up to here, say. Holes are stable here. And you have here a mount, here a hysteresis part. If you go up, you start with hexagonal cells, here, hexagon, and you go up to this point, and then you lose stability and go to holes. And when you come down, you will stay on holes until this point, when you lose the stability of holes and go back to hexagons. So it's this kind of behavior in a non-chaotic system, which is similar to what we see over there.
Yeah, but here this is a real hysteresis.
Yeah, this is real history. I mean,
sorry,
as I said, I mean,
Igor, in what sense is it here more real than in the other?
Sorry?
In both cases, because you said before it was not a hysteresis in the proper physical sense.
Yeah, because it's not in the same system.
Yeah, it's just here. It's just here. Yes, just here, not the same system because you changed. No, you changed the Rayleigh number.
There are two modes here. Two modes.
Yeah, but I don't see the difference.
Hexagon. One is.
Yeah, but you are changing the Rayleigh number. In the other case, you change the Prandtl number.
No.
No.
When you change Rayleigh number, you change temperature difference.
Yeah,
for example.
that's a parameter.
I mean, this is an easy control parameter.
Yeah, of course.
I mean, to use the Prandtl number as a control parameter is difficult.
Yeah.
I mean, it's not impossible to change the Prandtl number of a fluid by.
But it's not. It's in fact not a basic difference.
No, there is basic difference because you have the same systems, the same. Just you change temperature difference between upper and lower layer. That's it.
But
this is the
that
same
depends
system.
on your notion of the same.
Yeah, the same. I mean, you're arguing like an experimentalist.
Yeah.
Yes.
You can't change his
exactly.
fluid very easily.
But
You can change the temperature. But
Okay.
In another way, you can talk about, for example, changing a statistical mechanical system. For example, if you are in hard disks, you can change its temperature by changing the number of particles you have.
Yeah.
So that's like being in a grand canonical ensemble. But in an experiment, you don't generally introduce particles in your system, right? You think temperature...
No, I introduced in this experiment particles in the system.
No. While you are going through the problem. While experimenting, you can't keep on introducing particles. So, I mean, some things are easier to do in experiments. Some knobs are easier in numerical simulations. So maybe we can consider them both as just knobs.
Okay.
But I see your point.
Yeah, yeah.
This is basically right.
Perhaps.
No, it's true that this is applied mathematics, so
Okay,
who
but
cares
we
about
were
the underlying
physicists, no?
physics? No, but
Yeah, yeah.
that's
Yeah.
something I have already discussed with David Hughes. And when you are doing experiments, what matters is what you play with your knobs. It doesn't matter what it means in reality for the experiment.
Okay.
Yeah, I just want to show sort of pictures of these two different type of dynamos. Here is a strong magnetic field dynamo with a strong mean field. If you look at this, it's actually somewhat outside the outer surface, then you see a very strong dipole. I mean, it's hardly modified by fluctuations. And the difference rotation has been decreased so far that there is no longer sort of a Z-independent difference rotation here, like you see still in the fluctuating dynamo. Here the difference rotation is still the same kind as you see it in the absence of the magnetic field. But here the mean magnetic field, even if you go further out, is still highly fluctuating, and you still see a dipole, but it is modified quite a bit. And the mean toroidal field is indicated here. You see that here there's it has a strong structure, and this is responsible for eliminating the strong difference rotation, while here the field, this actually has a tendency to be somewhat hemispherical in this case, but it's not strong enough to eliminate the difference rotation as we of the geostrophic type as we see it in this plot. I mean, this is so far I wanted to talk about today. I think I will not take too much time from what Sasha has to say.
Oh, I mean, fine, it's very interesting.
I can talk about my reversals, but it's another story.
So you can't relate it reversals with the appearance of chaos in dynamical systems, yeah?
No, these reversals in my case actually have to do with oscillations I show, but the oscillations have the property that some of the oscillations do not affect the poloidal field. The poloidal field just has the same polarity, while other parts of the oscillations reverse the poloidal field, and this, whether one or the other thing happens, depends on random properties. But basically what I am claiming is that even the Earth is an oscillatory dynamo, and it oscillates on a period of 30,000 years.
But this, I thought that part of this, what you said, was also linked to the actual polarity of the field in the iron seed, I mean the solid one, and that if you are able or not to diffuse from the liquid part the poloidal field that you have into the seed, then you get an actual reversal. But if you in the liquid part, the reversal of your poloidal field, it doesn't last long enough to be able to diffuse inside the solid iron core, then you got only an excursion, and you see what I mean?
Yeah, but these ideas, I think, they have been expressed by Jones, and I don't see this in our calculations. Usually find very little influence of the inner core. I mean, it doesn't really affect what goes on in the outer core very much.
I'm surprised by that, because in our simulation with the tachocline that we did for the Sun, we did find that the presence of the poloidal field associated with the magnetic layers seems to have some feedback on what was going on in the convective shell. and could make the reversal less frequent than what we were finding in the simulation without the tachocline. So we do seem to find aspect of that as well in our solar simulations.
Yeah, but then you have to realize that in the sun, the core is huge. I mean, it's much larger compared to the convection zone.
Not in volume. In volume, they are the same.
But in the Earth, the core has less than 1/10 of the volume of the outer core.
Okay.
Yeah.
In terms of solar dynamo, that I think situation is quite different, because in the sun we don't see changes in differential rotation. At least we see only tiny changes, 10 to the minus 3, and we don't see changes in convection pattern. So what lessons can we learn from the simulations in terms of?
Yeah, I mean, here we
solar
don't
dynamo?
see any change in the different rotation. Really the same in both cases. I mean, especially
suppressed, and you were talking about suppressing differential rotation.
I mean, here you still have some different rotations. It's less than you would have without magnetic field, but it still has a shape as on the sun, for instance. I mean, it's a prograde on the equator and retrograde, say, near the pole.
So the change of the sign of the magnetic field doesn't change structure or velocity?
No, the velocity field is always like this.
Yeah, because for example, in simulations by Gary Glatzmeyer and Paul Roberts, we see clearly that when there is a change of the direction of the magnetic field, there is a strong change, I see the velocity field.
No.
Yes, fine. No?
The velocity field, I don't think it.
No.
I don't
No,
think
really?
It must not, no?
Maybe
No,
it was my
So
impression
reversal is linked
during
to
this
the
talk.
currents and
The
which
sign-
change
the
the
sign
current,
doesn't matter,
not
no?
of the flow itself. I don't think
Okay, maybe I understand.
So the percentage in change in rotation rate here, say equatorial rotation rate, how it change? For
I mean,
contrast,
it fluctuates,
but how much that we have?
but it doesn't
1%.
depend on the. I mean, I don't know how this actually it's equator. I don't think it changed by more than 10 or 20%. I mean, it's,
Well, still quite, that substantial number.
yeah, but
Because
I
there's
mean,
non-linear coupling between rotation and magnetic field. And on the sun we don't see this. So what
no,
we
I'm
see
not
some
saying that this
fluctuations.
is a solar dynamo.
Well, we see only some 10 to the minus 3 effect.
Yeah,
Because the oscillations and only.
Not only, I already showed you the work by, what's the name of the guy, but I have shown you that there is a trend of having a slightly larger differential rotation when we are in minimum versus when we are in maximum.
Well, it's 10 to the minus 3 effect, this. It's not like 10 or 20%.
yeah. I mean, this is not meant to be anything like the solar dynamo.
No.
My question is, what we can learn from this in terms of, here. Suppose we see a very, very tiny variation of rotation.
No,
we
and
still
what-
have
what we
dynamo in your simulations?
Yeah, I mean, the differential rotation is very different depending on the type of the dynamo you have. If you have a strong mean field dynamo,
Then you
you
kill
have
it.
the opposite sign of the differential rotation in low latitude and high latitudes from this case. So qualitatively there's a dramatic change there, and what do I want to say? I mean, the main thing of what we can learn here is that dynamos depend sensitively on the assumed effective Prandtl numbers, magnetic or ordinary Prandtl numbers. That's what I can say.
How general is this? Because it's only this type of dynamo, right? When you have this kind of coupling between rotation and magnetic field.
Yeah, I mean, it's perhaps when we have a weaker rotation, maybe we don't get this two different dynamos.
High magnetic resonance number.
So far we have gone only on to higher rotations, and where we still see the same phenomenon.
Yes, but I want to go back.
I was interested in your experience with the dependence on Rm of the toroidally averaged mean magnetic field. I think you told me at one point that you typically always find that the mean magnetic field's amplitude is actually decreasing with Rm, increasing Rm. Is that true and always true, or?
For which time?
Increasing Rm would be lowering of the magnetic Prandtl number.
If Reynolds
Yes.
number is fixed.
Yes.
Yeah.
Yes.
If we are-
But that's my point. I agree. I want to follow on that line because your statement saying that your dynamo change as a function of PR and PM seems to have hidden below that the idea that the RM and RE are changing. So my point is that if you now compute for given PR and PM, and you fix this PR and PM and increase your Reynolds and magnetic Reynolds number. So there is certainly a way of doing that you can keep that and probe different value of Rayleigh or Reynolds number. Will that statement be still true? I mean, you see, you play with different set of PR and PM at different value of RE and RM and change again and do that, you know, because I have the impression that hidden behind this statement on PR and PM is somewhere Reynolds number and RM number dependence. So I will be cautious on that.
Maybe this kind of dynamo is strongly different from the turbulent dynamo in the sense that it's not real mean field dynamo. This is some kind of nonlinear laminar dynamo, but of course with appearance of chaos in dynamical systems. And usually if you consider turbulent dynamo, large-scale dynamo, dependence on molecular values, parameters is very weak. I mean,
if you're in the asymptotic regime, I agree with you.
Yeah.
But we are certainly not in the asymptotic regime in any of our simulations. We are in the Earth or the Sun. Now, but my point is that if Fritz had a plot where he could show things as a function of Rm, then if I could have a curve at constant Rm or constant RE or both, and then I would be interested to see how the thing change, you know. Because sometimes you
But I don't think that is quite true.
okay.
Because I showed you
that's-
this plot where we plotted this sort of hysteresis as a function of the
Rayleigh number.
it's a Rayleigh number, and you see they just went parallel. I mean, we couldn't even go to high enough Rayleigh numbers because of numerical problems to see where they would come together or where one would disappear.
Yeah, but that's, I think, exactly a different statement because you are comparing the strong branch versus the weak branch.
Yeah, yeah.
But
I'm just saying it
your
doesn't-
statement is a bit different because here I thought you were implying that the PRPM was also changing the ratio, the property of the dynamo itself, not just the amount of magnetic energy. The dipolar versus quadrupolar or versus hemispherical. I thought your statement on PRPM was more in the nature of the field you get rather than on the amplitude of the field.
Yeah, I mean, certainly I agree but I don't think that this dependence on PR and PM really reflects a dependence on the Reynolds number and the Rayleigh number, because in terms of the Rayleigh number, things just seem to exist for any range here. I mean,
What you have a factor of 2 or 3 in terms of Rayleigh. That's it's not as large a range as you have in your PM and PR.
Actually, we have done more calculation now because this take more time, and I think we have no indication so far even over factor 10.
But in principle, if Rayleigh number will be larger than 10 to the 7, 10 to the 8, the picture will be strongly different. Maybe it will be more close to the situation with classical mean field behavior.
Actually, what we find when we go so far, we don't find dynamos anymore. They're just,
I see.
That's
There's a suppression of dynamo.
This flux expulsion thing, yeah, I would like you to go back on that because I think that's very surprising. I never found that in my simulation.
But
So
if you exceed, if you take Rayleigh number 10 to the 9, this really turbulent convection, I think you obtain that.
No, I don't see why.
No?
You should still get a small
There
scale
is a s-
dynamo. I'm surprised.
Well, at
Perhaps
least
not
we
a large
see-
scale dynamo,
no.
but a small scale
Yeah,
dynamo. I'm
but-
surprised
yeah,
you lose
but-
it.
Maybe convection without rotation. We see, at least in experiments, that there is a difference between convection below 10 to the 7
Yeah, you are
and
speaking
convection
of,
with a Rayleigh number 10 to the
Yeah, you're
11,
speaking-
10 to the 12.
you are speaking
There is
of hard
difference.
turbulence.
Hmm?
What the word of Castan and others that are
Yeah.
French guys, they have called that hard turbulence.
Yeah, yeah,
You know?
exactly.
And the dependence on the Nusselt number change and all that stuff.
Yeah.
But I
Okay.
think I'm not sure that this will still make a difference in the dynamo. So what happened in your simulation that you quench the dynamo as you become more turbulent? That's very surprising.
Now, yeah, I mean, it's perhaps not so surprising if you realize that you may not see any of the small-scale generations then, because that would need a numerical resolution much higher, and we just feel that I mean, first of all, if you have a very strong convection, very high Rayleigh number convection, the effects of rotation go away. You don't have this organization of the convection in terms of columns,
Of course.
and you don't have this helicity connected with the columns. I mean, that is certainly good for dynamo action. And you lose all of this. And that's perhaps not only the flux expulsion, but also this diminishing helicity, which does not allow dynamo action anymore. And so that's what you find.
Well, but okay,
Okay.
that's something I think is of interest that we discuss a little
Yeah.
bit more.
Okay, thank you very much for a very interesting lecture. Maybe we'll have 5 minutes break because we are tired. Yeah.